Greetings, folks. Welcome to the live stream. We're here live on YouTube. This is where you can drop in comments, but we're also streaming on X, Trellis Research, and streaming as well over on LinkedIn. For the first time on the Trellis Research page on LinkedIn, we went over, when I say we, I mean Trellis Research, went over 150 followers, which is needed in order to live stream. So a few quick news items today. I'll just briefly touch on an updated model that Mistral have just brought out, the 7B model, and I'll make a few comments on Phi 3. They've just released a vision model and they're releasing larger models than the mini model. So there's now a Phi 3 small and I believe a medium. And the purpose of today's live stream is going to be to talk about LoRA fine tuning. So I'm going to take us through all the way with your questions. I'm going to take us through all the settings for doing fine tuning. Howdy, Yugi. And let me know in the chat here if you're on YouTube. I'm not sure if you can comment if you're on LinkedIn, but let me know, say hello if you're in the chat. Let me know if you have any specific questions on today's stream. You can see here the agenda. I'll very briefly touch on full fine tuning, then go through LoRA, and then batch size, talk about data set sizes, learning rate scheduler, and then maybe a little bit about some examples I've run in weights and biases. Howdy, exploring. Thanks for joining. Let me know, folks, if you're in the chat, and let me know of any questions that you want to add in. Welcome also to those who are going to be watching this live stream later on. So I was scrolling Twitter and a few updates I want to bring to your attention. So Mistral have made a minor release on their 7B model. It's a minor release, so there's nothing majorly different compared to the V02. But what it does is tweak the tokenizer, and it's really only tweaking the tokenizer just because it's supporting function calling. So now you're able to use the Mistral model out of the box for function calling, provided you use Mistral's libraries. Let me just increase my screen size a little bit here. So you can see if you import transformer and generate from the Mistral library, you're able to make a call to the LLM that includes tools. So here are the tools, somewhat like you would for OpenAI, and then you can feed in the messages. So I think this is probably smart for Mistral, encourages people to use their API as opposed to using the OpenAI style API. So I'm wondering if that's part of the reason they put out function calling. Of course, it's a very popular requested feature. A few questions here. Any perks to join the channel? Any extra materials? Not sure what you mean by joining the channel. Let me know what you mean there, exploring. I'm not too sure. Yugi's asking about, without unslots, can we merge the adapters and base model? Yes, this is actually possible now. I think if you look at Trellis blog, you'll see me answering that question. I don't remember, it's probably a few weeks ago, but I talked briefly about, yeah, I don't see it, but if you look through this, it's on one of the blog posts, and you'll see there how you can merge without using unslots. So it is possible to now properly merge quantized adapters, rather adapters into a dequantized model. Yeah, that is possible, Yugi. Okay, and we have a question here on, can I create a video how to increase the context length using rope? There is actually quite an old video now, maybe 3 to 4 months old, that touches on rope. I think it's on either the Yi model or maybe on extending the Llama model, but there is a video specifically on increasing the context length. So you might want to check that video out. Should be available if you look through the videos on YouTube, or if you look at trellis.com/advanced fine tuning, you'll see if you scroll down, there should be one on fine tuning for context length. Is it possible to merge 2 adapters from 2 different trainings of LoRA? Yes, it is possible. You can just merge one, and then you have that merged model, and then you can load another adapter, and then you can merge that second adapter. So yes, that is possible. Just to round out the news section here on Phi 3. So this is a model that's been released now in multiple sizes. Phi 2 was released, I think, either earlier this year or last year, and it was quite a powerful model, but it basically uses a lot of data from GPT-4, GPT 3.5. So it uses a lot of synthetic data. So it's almost as though, well, it is as though this model is being trained on kind of stronger language models that provide very clean data. And so here you can see they've now released Phi3 in mini form, which is a few billion parameters. Then there's also small, which is about 7 billion, and medium. Let's check actually how many parameters is medium. And there's this instruct model, which I think is a 4 billion parameter instruct model. So it's got an encoder for vision and connected onto that a language model. Let's take a quick look here at the medium model and see what size it is. So it looks like we have 6 files of about 4 or 5 each. So it looks like about 30 gigabytes of size. So I assume it's probably about 14 gigabytes in 16 bits, 2 bytes per parameter. So it looks like the medium model is out now. And 2 of the unique features of this Phi collection, one of them is it's 128K context, and then also this ability to do the vision model. Now, just a few things. There have been a lot of issues with making GGUFs, so it's been very difficult to run in quantized form on a Mac. There's been a lot of discussion on the Llama CPP forum about that. I don't think it's quite been resolved yet. The quality seems to be quite poor when you try to quantize this 128K model. I've been trying to make a function calling version, but yeah, I'm being bottlenecked on being able to make the GGUF there. Something else to note is that when one of these models comes out, particularly vision models, they're often not readily supported by VLLM or TGI, which means even if you fine-tune them, it's not going to be easy to do inference on them, at least at scale, until they're supported. So yeah, often you have to check, is there going to be good support? And there may or may not be. So that's a quick rundown of some of these models here. I do want to also caution that Phi, because it's fine-tuned on this GPT-4 type data, it tends to overfit a lot of the evaluation benchmarks. There may just be a lot of benchmark data within the data set for fine-tuning Phi. And what that means is the performance looks pretty good, but then when you use it in applications, it tends not to be quite as good. I can just show a snippet here. There's a piece, GSMK. So there's this test you can do on language models. It's like high school maths, and basically it's called GSM8K. That's a standard test for doing maths. But one of the issues is that a lot of the models effectively have some of that data in their training, and so they'd score well on the model, even though the model is not really doing well. It's just repeating back what it's been trained with. And so there's this team that's come up with GSM1K, which is like their own proprietary version or private version of the same maths tests that they haven't released. So there's no way the models can overfit on it. And so by doing that, what they were able to do is see how much is the performance of these models overstated. And if you look at this graph here, you can see basically what's the gap between kind of the public eval metric and the private eval metric where you can't overfit. And you can look through the models here, which I know will be small on your screen, but you can see that Phi3 mini for instruct, it's like, yeah, it's like really, really different. So Phi looks really good in the benchmarks, but it seems to be overfitting. It just seems that there's quite a lot of data in the training set. So that's not really representative of performance. Somewhat disappointingly, Mistral 8x22 also seems to very overfit the data, which means the performance is probably overstated. By contrast, some of the strongest models, GPT-4 and Claude 3, they actually don't seem to overfit at all. So that's probably a good sign, a good testament to the strength of the models. Anyway, I think this is a very nice piece of work, and it's helpful to look at this to determine if the model is going to be strong or not. With that, we're going to head back to our main topic for fine-tuning. And I'm going to start off and just talk through a little bit full fine-tuning. And then I'll take you through LoRA and how we apply adapters. And along the way, I'll review some of the slides explaining kind of in a graphical way what we're doing when we're fine-tuning with some plots like this right here. So what I'm going to do is use a specific model as a framework when I'm doing this. The model I'm going to use is Tiny Llama, just because it's small and I can work with it very quickly. And I'm going to use that model to print out the models, the modules, and apply LoRA adapters, just so you can see exactly what I'm doing. Now, just give me a moment here because I need to log in to my Hugging Face account. And it looks like I have possibly run out of credits. So I'm just going to connect to T4. Just bear with me 1 second. Unfortunate, I literally checked right before I joined the stream and saw I don't have any credits left. So let's see how this goes. Sorry, my camera's going to go wild for a second. And I just need to approve the payment to Google, send some euros over to Google so that we can continue to learn. Okay. So hopefully we'll be back in action now. Yeah, you can see I was getting some kind of a message. Okay, so sorry, I was just topping up my credits here. What do I think of Google VLM Polygem? Oh, I haven't heard of that one. Can you put a link in the chat to the language model you're talking about there? Hey, Ashish. And yeah, by the way, this is one of the problems with Google Colab. Not only do you run out of billing credits, but also sometimes the sessions just crash. And so you can be in the middle of training and it crashes and you have to kind of reload stuff. But yeah, drop that model in the chat. In the meantime, we can get going here. So I'm going to install transformers, HF transfer for fast weight download. You could download flash attention, but I'm not going to do that because it's a tiny model. So it's not really important that I speed things up too much. Next here, I'm just going to enable the fast transfer by setting an environment variable. And then I'll load the model here. And then I'm going to load the tokenizer and print out the model. And since I did this earlier, I can just keep talking here. So you print out the model and you see a list of all the modules. And here we have the embedding layer, which is going from the input tokens into vectors. So it's converting tokens like cat, at, dog into specific vectors. Then we have 22 transformer layers, each of which have attention and multi-layer perceptrons in them. And then we get to the output and we have the language model head, which goes from vectors back into the individual tokens because we need a final token. That's what we're trying to guess, the next token. So these are the modules. And the whole point of full fine tuning is that we want to fine tune all of these modules. So everything here, embed tokens, this is one matrix. Well, you can think of it as a matrix. Each of these layers here, they each have matrices for Q, K, V, O, rotary embeddings. So these are all matrices we're going to train. Then there are matrices in each of the multi-layer perceptrons for gate up, down, activation. Then there are parameters for layer norm, post-attention layer norm, and then LM head. So in full fine-tuning, you're fine-tuning everything. You're literally allowing the model to update everywhere. And yeah, that requires a lot of GPU memory because you need to fit all of these matrices into memory, but you also need to fit gradients for all of these matrices into memory. And you need to fit optimizer parameters. So you need to fit a lot into memory. So that's not usually what we do. Instead of fine-tuning everything, what we do is we actually freeze all of these matrices. So all of these matrices that are in these modules, we freeze them. And instead, we select certain modules. So we say, okay, we're not going to update all of this, but maybe we'll update Q projection. So maybe we'll update this set of matrices in the attention layer. And instead of updating it, we're actually going to update these smaller adapters, which are called low rank adapters. And they're called low rank because they are smaller in height, or the rank of the matrices, the adapters, is smaller than the original matrix. So for example, we might replace the size here, or not replace, but add onto this matrix here two adapter matrices, which together, if you multiply them, so they're 8 by 1024, if you multiply them together, they'll expand to make a matrix of this size that we can add on top at the end of training. So the whole idea of LoRA is to train these small adapters and then merge them in at the end, which is the question around merging we were getting at the start of the video. So this is LoRA, and as I said, it's common not to apply LoRA to all of the matrices, but rather to apply them to just specific layers. And the specific layers we often apply to are the attention ones and also the linear layers here. Now, these are the vast majority of the parameters in a language model because there are 22 times all of these matrices. So these account for a big majority of all the parameters. A smaller portion of the total parameters is accounted for by the embedding layers and also the LM head, which is going from vectors back to tokens at the end. So this is what we do in LoRA. And I'm not going to talk about quantization today. I just want to focus on LoRA because there's kind of enough to talk about there in terms of optimizing. So I'm now going to implement that in code. So what I'm going to do is set up these adapter matrices for specific modules within this model here. So let's do that. And we can just take a quick question here. One doubt why we should left pad prefer while using flash attention. Yeah, flash padding side. So yeah, when you're training, often you have a certain length that you're feeding into the language model, and all of your input sequences are not exactly the same length. And so in order to make them the same length, you add these kind of dummy tokens. And in place of these dummy or pad tokens, you basically tell the computation when you're going forward to just put zeros there. So like ignore basically those positions. That's the idea of the padding tokens. And you can put them either to the left or to the right. And yeah, I actually don't think on the spot I would be able to get into the full sum of reasons for why you go one way or the other. It actually depends on quite a few things. Flash attention can have an effect. Using unsloth can have an effect. Specific models like Quen can have an effect on which side is better. So I don't have a generic rule on what to do in general. Unsloth will set the side of the padding automatically, so you don't have to worry about that. Otherwise, with flash attention, you'll get an error if you're padding to the wrong side. So you can just check the error and then you can flip it to the other side. And Yugi is saying Moondream has left side padding. Yeah, I've kind of seen both. I think left side padding is maybe a bit more common. But yeah, if you think about it in terms of what the model is seeing, if you left pad, then there's not going to be any extraneous tokens after the end of the completion. But there will be extraneous tokens in the input. And potentially the issue there is your attention is paying attention to those early pad tokens if you're left padding. But you should have a loss mask. So the attention should really have a loss mask that's ignoring those tokens on the left-hand side. So it shouldn't really make too much difference if your attention is set up properly with the loss mask, and that should be handled properly by SFTTrainer and the data collator. Now, there's another reason why padding might make a difference, which is that padding, like the position where you are in the sequence, it actually matters. So ideally, when you add positional information to embeddings, it would kind of be agnostic if you slide your inputs anywhere within, say, a fixed window of 1000. If you've got an input of 30 tokens, it should be agnostic if you slide the inputs anywhere on the 1000 spaces with padding tokens. But actually, it's not quite agnostic. The cosine and the rotary embeddings, there's still kind of some positional information embedded, it seems. So you do get some effects like that intuitively I can't really explain why it would be better to put them at the start or the end. Like one way to think about it is that language models can sometimes naturally be good with stuff at the start of the sequence, because in natural text, we tend to put summaries at the start of books or at the start of patents, or even just general articles. We have an introduction and a conclusion. So the model can be strong at the start and strong at the end naturally. And so for that reason, like you can come up with arguments for why you might want to have your context focused there in one place or the other. Okay, that's probably more than you wanted to know, especially without a specific clear answer, but gives a little bit of context. So let's go back here and start to apply the LoRA adapters. for which we need to install PEFT, parameter efficient fine tuning. And it's parameter efficient because instead of fine tuning all of the parameters, it's efficient. It just fine tunes a few of the parameters. So that's installed now, and we can move to setting up the LoRA configuration. So there are a few things we want to talk about here. Hey, Loic. We want to talk about rank. And by the way, somebody should have asked for a copy of this notebook, which I'm going to provide now. So let me just unrestrict it, copy the link, and throw it in the chat. A few things we're going to talk about in the LoRA configuration. So first, the easiest thing to talk about is this target modules. And this is what I already said. We're not going to fine tune all of the modules. We're just going to fine tune some of them. So here you can see I'm picking out Q proj, but I can also add in some others, like I can add in K proj. And the way that I know which ones to add is by printing out this print model. So this is a very important step. If you're looking at a new model, you want to print model once it's loaded, so you can see what's in the model and decide what actually you want to fine tune. And you want to keep an eye out for the self-attention. It'll be called something like ATTDN, and MLP, which might also be called feed forward, but probably MLP. MLP is a type of feed forward. Feed forward could just be a linear layer of matrices. MLP is a sandwich type approach where you have two linear layers with an activation function in the middle. So yeah, typically if you're fine tuning, the more data you want to fine tune with, then the more parameters you probably should make trainable. If you are only fine tuning with a small amount of data, you might get away with just fine tuning one set of modules. But if you really want to add a lot of data, then you're going to need to fine tune more of the modules. So here I've just added in two of these modules. Typically, if I'm fine tuning for something like function calling, I would decide to make usually all of the attention and all of the MLP trainable. You could actually just do one of those and it works fine as well. So that's what I do for function calling. If I'm chat fine tuning, then I need to also make sure the embeddings are updated. So LM head needs to be updated, and also the embed tokens. And that's because you're changing the positions of special tokens when you're chat fine tuning. So you need to provide those updates. And there's a specific way of doing that, which is called modules to save. So modules to save is basically for full fine tuning specific modules. So it's basically saying, okay, I've frozen all of the modules here. I've applied LoRa adapters to Q and K, but you know what? I actually do need to fully train some of these modules. I do need to fully train LM head, and I do need to fully train embed tokens. So that's what modules to save is. And it's going to allow us to fully fine tune specific modules. Now, why do you want to do that? Well, the main reason you want to do it is because you need to update the embeddings. Either like the language is different, so the embeddings are going to change significantly, or you're moving around special tokens, as I said, for chat fine tuning. And why could you not just do LoRa? So like, why couldn't you do LoRa on LM head or LM embed? Well, they're not linear layers, and the PEFT library is set up for doing LoRa's. So it's set up for automating this process of creating these adapters. It's set up for doing that on linear layers. So quite simply, probably you could find some way of like some LoRa analogy that you could apply, but it's not straightforward to do it to LM head or LM embed, to embed tokens or LM head. And moreover, embed tokens you can think of as a dictionary. It's really a mapping from those original tokens like cat and a onto vectors. It's not so much a transformation in space like these linear layers. So these are different in how they're structured, and that's why LoRa is more conducive to set up on these, and that's what's supported by PEFT. Okay, let me know if there's any questions on that, because I've just explained now modules to save, and I've explained target modules. Now, a few of the other parameters here I'll just touch on. So LoRa dropout. Dropout is where you turn off certain neurons within LoRa. So even within this matrix here of 1000 by 8, you're going to pick specific weights in the forward pass, and you're just going to turn them off. So you're not going to have any signal going through those neurons. And the reason is you don't want to overfit your data. So adding in dropout is basically a technique to prevent overfitting. And I don't think it's supported if you are using unslot, by the way. So you'll just see that set to 0. So next is bias. So when I talk about a matrix here of 1000 by 8, let's say, often this is it's a series of numbers or a matrix of numbers that are going to be multiplied. But this is an oversimplification because often you do a multiplication, but you also do an addition. So you do something like, where can I write here? Can I write here? Why not? So instead of doing something like y equals mx, y equals mx, wow, that's really hard to see. Okay, instead of doing something like y equals mx, often these matrices actually have a bias c. So it's like an affine term instead of being linear. So yeah, having a bias is fairly common, although it's also fairly common to just not bother with a bias. And sometimes that can reduce parameters and also just improve stability in some cases. So sometimes language models, they'll include biases within these layers, sometimes they won't. And what this parameter here does is it says, okay, even if we're applying LoRA to this module here, we're going to freeze this base model, but we might still train the biases. Or we might train the biases only on the modules where we apply LoRA. So there's a few options for what you can set here. I have never turned this parameter on, but just so you know what it is, you could train the biases. I think you can do something like only LoRA, or you can do something like all. I'm not quite sure. You can check out on the transformers documentation. Either way, I set it to none. Unslot doesn't support it either. So yeah, let me go through, and then just the last one here to knock off, task type. Yeah, we're doing a causal LM, so we're in a causal process where we're predicting the next token. So that's why we have that set there, which is something you're always going to have if you're using kind of llama type models. Now I want to talk about rank and LoRA alpha, and I want to talk about use RS LoRA, which is rank stabilized LoRA. But first, let me take a few questions. So, hey Damon. So Joao is asking how to pick the perfect targets. So let me just quickly run through that again. If it's a very small data set, 50 to 1,000 rows, you can often keep the number of targets low. You can potentially just pick all the attention or all of the MLPs. If you are going to fine tune with say 10,000 to 1 million data points, then probably I would select all of the linear layers. So I'd select all of these attention layers and I would select all of the MLPs. If you are fine tuning for chat, where you're changing the chat template, which means moving special tokens, then I would, you can't target them with LoRA, but I would add to save modules, the LM head and the embed tokens. And furthermore, if you really want to get kind of the full span of fine tuning, you could even make the norm and the post attention layer norm and the input layer norm trainable as well. And that, I believe, can be done by adding them to modules to save. So I think that's a bit similar to the question here for Loic. What layers do you train to learn the jargon of a use case for official, for example, to learn jargon for a use case? Yeah, so actually I recommend, if you're interested in digging deeper, you can look, there's a video called REFT, so representation fine tuning. And in that video, I do another kind of fine tuning, but I also do LoRA. And what I do there is I reduce the number of modules to something really small, like just fine tuning, say QProj. And not only that, there's a parameter you can specify within the LoRA config to only target a specific layer, like layer 15. Now, if you want to fine tune encode like very specific information into a language model, you can basically narrow it down to just one layer and just one set of matrices. And you can actually fine tune for many, many epochs, which will result in overfitting, but it will also result in ingraining that information into the language model. So basically there's this option where you can kind of store small amounts of information in a very specific location of the language model, just by being extremely targeted, which is quite a different approach. Now, I'm not sure if that's what you're asking for Loic, although that would be possible if you're trying to ingrain, I don't know how much information people have tested it on, but probably you can ingrain, thousands, if not more words. maybe even much more. But if you're trying to memorize over like large document sets, you're getting back more towards traditional fine tuning, and you're going to want to target probably a large number of modules. Okay, when we choose causal LM in LoRA config, do we have completion in SFTTrainer? So I wonder, Yugi, if you're asking about whether we're training on completions only or whether we're training on the prompt plus the completions. We can talk about that, let me know. And hey, Udim, you're asking what do you recommend fine-tuning for low resource language? I actually just made a video this week on that. If you check out my video on the Wikipedia dataset, I'm trying to fine-tune on Irish, which is a very low resource language. And I create a data set for it, and you can see the parameters I use. I fine-tune a very wide set of modules is the answer. So I target all of the linear layers, and then I save the LM head and the embed tokens. Now I used Unsloth, and I don't think Unsloth necessarily allows you to save, to add to module to save the norms. So I'm not fine-tuning the norms, and that might actually be a drawback. I'm going to make a video that will add to the Wikipedia Irish data from using Common Crawl data, hopefully fairly soon. And I might there actually use the traditional, not Unsloth trainer, so I can train the norms as well. Yeah, so you're asking prompt plus completion. Yeah, we'll get to this in the trainer, but when you're training, you can penalize the model based on all of the prompt. So you can penalize it based on question plus answer, or you can actually target the penalty to just be based on the answer. And that can actually speed up fine tuning, especially if you have like really long prompts and you want very specific behavior in the answer. It can be pretty good if you target the answer. That works well for function calling. It works well for structured training. And yeah, I will try to show you when I get onto it on the trainer here. Okay, question from VastCNC. Is there a best practice for code assistance on a programming language outside of JS or Python? Yeah, I like this question. It's like the minority language, and it's something somebody mentioned to me yesterday. I think probably something similar to what I did for fine-tuning on Irish. So I think the low resource language is kind of a similar question class to fine-tuning for code. Oh, just one thing. You'll notice in my video on the low resource language, the Wikipedia video, it's pretty important that you blend in a small portion of data that is representative of the original language model's data. So if you're fine-tuning on Elixir, I don't know, is that a coding language? I don't know it, it probably is. But if you're going to fine-tune on Elixir data, you want to blend in like 5% of other coding languages like Python, C, or whatever. And the reason you want to do that is to avoid catastrophic forgetting. Yeah, because if you don't blend any data, your model can just start to have its original data overwritten. What happens on the optimization curve is that you're kind of here and you're now optimizing for Elixir, and Elixir is kind of pulling you over. Let's say it's pulling you over here, but really you don't want to be pulled over here because you need to be in the vicinity of here to be still doing C programming. And the idea of including like a 5% blend, that means you're going to have 1 or 2 samples in every batch of 32. And that's going to kind of tether your model to where it was on the learning curve. So yeah. All right, so let's move on here. And I'm going to actually go through this and then kind of talk about how you pick the rank and the LoRA alpha. And then I'm going to talk about using rank stabilized LoRA. So did I run this cell? Okay, I've got the LoRA config and I've got this. Now, I highly recommend always running model.print trainable parameters. This tells you what percentage of the total parameters are trainable. Now, just to be clear, the total parameters will be larger when you apply adapters, because now you still have the original parameters, even if they're frozen, but you have some extra adapters. Now, I'm not saying they're trainable. I'm just saying, sorry, these are all the parameters. All the parameters, that number is larger when you apply adapters. And this trainable percentage is the percentage of the all parameters. Now, in this case, we have only chosen we have only chosen to train the gate projection, the K projection, and LM head and embed tokens. And I'm going to, so my question for the chat is, why do we have such a high percentage of trainable parameters? Why? Usually in LoRA, this is really low. It's usually like single digit, low single digit, or even point something. Why is this even 10%? Anyone have any clues why it's that high? In the meantime, high resource language. I mean, I think the rules probably apply somewhat similarly for Portuguese. Basically, if you're fine tuning for a language, like, you're going to need a lot of data. So you're in the high data category. You're not in the low data structure generation category. So even if you go Irish, Portuguese, pretty much any language, you're going to need quite a lot. Okay, Loic says embedding. Yes. Okay, this is one reason. So modules to save, Yugi's got it as well. So let's do this. Let's comment out modules to save and see printable parameters. Okay, so trainable is now 0.14. So that was correct. Now this number here, it's going to be affected by what we choose for the rank, because the rank is setting the size of the adapters. So if we make these adapters bigger, instead of making them 8, let's make them 128. Let's see what that does to the trainable parameters. 2.23. So makes sense. We've more trainable parameters if we make the rank larger. And having more trainable parameters means we can fit larger data sets. So you can see there's going to be a big lever to think of. The lever is how much data do you have. If you have a lot of data, and you can think of a lot being a lot relative to the original data the model was trained on. So if you have a lot of data relative to 1 trillion tokens or a few trillion tokens, then you can start to use more parameters, because you need to have more parameters to fit that data. You can also train more modules because you need to have more parameters to fit that data. So broadly speaking, more data means you're going to target more modules, and you're also going to use a larger rank, so you can make sure to fit that data. So if I'm doing something like function calling, you can often get away with 8. If I'm doing language, Portuguese or Irish, I think I went with 128 in the video this week. You could even go 256, but that's how you increase the ability to fit the model. Now, any other ideas why, like, this is still very large? Like, I'm on a rank 128, but that's not particularly high for LoRA. Why is this number here still pretty large? And I've turned off modules to save. Any clues on that one? Andrew, hi. Yes, this is great. I'm glad you made this comment, Andrew. So if you use too high of a rank and you don't have correspondingly high amounts of data, you're just going to overfit. And that's the same reason that full fine tuning can be problematic. You end up with so many parameters being updated that you just kind of set the model off kilter. If you're fine tuning with less parameters, that means you can move faster with the fine tuning and it's more smoothed. So yes, if you're using small amounts of data, like for structured responses or function calling, if you set your LoRA too high, you can just get overfitting. Okay, any other clues on why this value is fairly high? So the reason is we're using a tiny model, tiny llama, and two things are different in smaller models. First of all, the base matrices are smaller. So when you decide to use a certain rank, well, that rank, it's really the rank relative to what the original matrix is. So if your original matrix is like 10,000, then if you go with a rank of 8, that's a very drastic difference. But if your original matrix is 1,000, then it's going to be 10 times less. So the rank in some ways is relative to what the original size of the matrix is. And when you look at a tiny llama model, basically in the middle, all the middle layers are a lot smaller than something like llama 70B, but you still actually have usually the same size embedding layers. So that's why when we turn on the embedding layers here and calculate the trainable parameters, that usually is going to be a really large number, because the embedding layers basically going to be the same regardless of the model size. So it ends up being a very large percentage. Now, what did I do there? I was missing a comma. All right, we'll keep it at this, 2% trainable. And I want to move on and talk about now choosing LoRA Alpha, which is a nice segue here for Andrew, because it's true. The rule that actually I was using for quite a long time, up until about a month or two ago, is you use LoRA Alpha equals 2 times the rank. So that's kind of the rule of thumb. And actually Andrew's rule of thumb seems to be the rank divided by 2 was rank over 2. I actually can't even remember if it was rank over 2 or 2 times the rank. I don't really know. But here's basically where the thinking improved, and where the thinking improved was around a paper on rank stabilized LoRA. And this gives some empirical, it's not really fundamentally theoretical, although I'll give you some intuition behind it, but it gives some empirical basis for how you should size LoRA Alpha. And so if you use RS LoRA, use rank stabilized LoRA to true, you can use the following kind of logic I'm going to propose for how to set alpha. And the logic is as follows, and we put it in a code box. If you have a model with a lot of training parameters, then you need to be careful at how quickly you update. So you need to take small steps along the optimization curve. But if you have a model and you have just a small number of parameters being updated because you've got a low rank and because you're just fine-tuning a few modules, then you can kind of move more quickly. So you can set your learning rate to be a bit higher. Now, it's important to realize that when you are fine-tuning, the learning rate that is applied to the adapters is actually different than the learning rate that is being applied to the base matrices. So let's write this out a little bit here. Learning rates. Maybe I can increase my screen a bit temporarily. Scroll down. So we have the base learning rate, which let's just say we're going to set it to 1e minus 4. That's learning rate that will be applied to all of the modules without LoRA adapters. So any modules to save, LM head, embed tokens, those base modules are going to have the rate of 1e minus 4 applied to them. But the adapters, what's the learning rate that's applied to the adapters? Well, the adapter learning rate is going to be equal to the base learning rate, but it's going to be scaled. And the way it's scaled is by multiplying it by alpha and dividing it by OR. That's how it works. That's just how it's set up. So really, what you're doing when you're setting alpha is, relative to OR, you're controlling what the learning rate of the adapters is. So if you go back to the rule of thumb, and now I remember, it definitely was 2 times rank, I'm pretty sure. So the rule of thumb on alpha was, it was basically set it to twice OR, because if you do that, you will set the adapter rate equal to the base rate multiplied by 2. So that's why this rule of thumb kind of works, because it basically says, I'm using LoRA adapters. I know that if I'm using adapters, I'm training less parameters. Because I'm training less parameters, I can go faster. And let's go faster by a factor of 2. So that was the logic of the original rule of thumb. But then RS LoRA comes along. So let's just write this as base rule of thumb. Then rank stabilized LoRA comes along. And what rank stabilized LoRA realized, that paper, is that actually everything scales with 1 over the square root of the rank. So actually, instead, what you should do is you should set things up so that the adapter learning rate is the base learning rate. And you should have that divided by the square root of OR. Okay? And up front here, you should have some constant, which is going to be alpha here. So this is the kind of equation that rank stabilized LoRA sets up. So it says that actually, as OR goes up, that's more parameters. So you should be slowing down your learning rate. Okay, we got to be more careful if we're training more parameters. So it should be square root of OR, and that's an empirical finding. So the question now is, okay, if we follow the logic of rank stabilized LoRA, well, what should we set for alpha? And here's the follow-on logic for setting alpha, which, by the way, you could certainly criticize, and I'd be interested in other approaches. This is kind of what I came up with intuitively. I think it's reasonable, but definitely open to criticizing on it. So here's my logic. Well, let's say we're fine tuning here with an adapter. And let's say we keep increasing the rank until the rank is actually the same size as the original matrix. Okay. Well, if the rank was roughly the same size as the original matrix, then really we should just be using the same learning rate. Because remember, the learning rate should just depend on the number of parameters. So if our adapters were the same size as the original matrix, which of course makes no sense to do, but if it was, we should be using the same learning rate. And so this basically tells me that we should set alpha so that it's equal to square root of OR, where OR is roughly the size of the original matrices. So alpha should be roughly equal to square root of OR, where OR is the rough size of the original matrix. Okay. Now this is kind of a loose way of thinking because not all the matrices are exactly the same, but you can go into the configuration of models like say here, Mistral, and you can take a look at the configuration file and you can see here we have some sizes and some of the characteristic sizes. And we want to take the smaller size. Like if there's a matrix that's tall, you want to take the lower one because we're interested in the rank of the matrix. So the maximum rank is always, the rank can never be larger than the lowest dimension of the matrix. So you can see for this model, it's one characteristic dimension is 4000. For llama, tiny llama, it's a smaller number. So basically we should be taking some number where alpha is square root of OR. And sorry, by the way, this here is not a code block. That's fine, just don't run it. So let's set up alpha being equal to, actually can't remember. I think in Python, it's like something like this. So we're going to set OR, but we're going to set it to some value like 2000. And I don't remember how to do powers do I do it like this? Somebody let me know in the chat. Take me out of my misery. And alpha. Yeah. So if your characteristic dimension is 2000 and you square root it, you get an alpha value of like 44. So basically what I'm saying is 32 is a pretty good value for alpha. And if you turn on RS LoRA, that's pretty much all you need to do. Now, if you're training a larger model where the characteristic matrix is not 2000, it's 4000, you can probably justify going with a larger value of the alpha. So anyway, maybe that was a bit much, but it gives you some context, some empirical context on how you might choose alpha. And that's why you'll see in my videos, nearly always now, I just have LoRA alpha equal to 32, maybe 64. It's a very big model. And then I set RS LoRA to true. And the way I pick the rank here is if I have a ton of data, then I decide to set the rank really high. If I don't have much data, I set it low so that I avoid overfitting. All right, so we've gotten the model and we're going to move on to the trainer, unless there are any other questions. Cheers, Ed. Appreciate it. Like, what do you think of applying different learning rate? Yes, I like that a lot, actually. It's called LoRA Plus. So there are two matrices that are the adapters. Why are there two? Because you need them both to expand out when multiplied to get back to the original matrix so that you can kind of cleanly snap them together at the end. And yeah, the way that you set them up originally is you initialize one of them to zeros because when the training starts, you need the model to be equal to the original model. So this product has to be 0 at the start. You don't want to start it at some randomized non-zero value because you'll be starting the model off training just knocked off kilter. So one of the matrices, and in principle it could be either, but typically it's the B matrix, which I don't know if I've used. Yeah, the B matrix here. And then the other one is initialized randomly. And because one of them is 0 and the other one is random, it actually makes sense to use a higher training rate on the one that's 0 because it's got more catching up to do. So this is why it does make intuitive sense to speed up the training rate of the second one. Now, one of the issues is if you do just multiply one of the matrices by some factor to accelerate it, that's doing two things. It's getting a relative speed up, but you're also just increasing your learning rate, which is having its own effect, which might be good or might be bad. So it's hard to pick apart if you just multiply one of them by a certain learning rate. So one of the tricks I've seen, it's a guy Vic on X, I saw him write this, is that what you can do is increase the A matrix learning rate, decrease the A learning rate by a factor of 8, he says, and increase the B learning rate by 8. So you're kind of, you know, doing it in a more balanced way. And that's maybe a bit more apples for apples. So yeah, I cover LoRA Plus in a video that's called, I think it's in the video I did on DORA, which honestly, I don't find much improvement with DORA, and there's mixed results in papers. And I didn't find much improvement with LoRA Plus either, but I didn't use that kind of up-down approach. I just increased one of them, so it wasn't a great comparison. But yeah, in principle, I think this makes sense. The reason I don't do it is because it's not easily integrated into the library for SFTTrainer. So you have to write a custom, learning rate custom optimizer module, which I do in that video. But yeah, it's a bit of a pain, so probably just don't do it. Okay, Joao came back and missed the good stuff. Why is alpha 32 not R times 2? Because I'm using RS LoRA. You can watch back. I went through an in-depth explanation. But yeah, you basically want to set alpha considering what the training rate would be when R is equal to the original matrix size. That summary is never going to explain it for you, but you can look back at it. So let's do a very quick training. How are we doing on time? We've 10 minutes. So I'm going to load a data set here. I'm loading Trellis. I need to install the datasets module first. And I actually need to install TRL. Now, why is my datasets module? Let's just code here. Pip install datasets. So just a note here that TRL, which is the library for SFTTrainer, SFTTrainer is great because it does a lot of work for you. But yeah, TRL currently, it's kind of changing its configuration. So it's using SFT config in the latest dev release. So here by doing git plus, I'm installing from the dev branch, which is the latest release. It's not great that I'm doing this because the dev is going to be unstable, but it does have the latest updates. So I've been using it. And update and install, not update, but install datasets. And now I'm going to load Trellis Open Assist. What is this? This is a dataset that I made from the Open Assist chat dataset, but I've just formatted it so it's Llama 2 style. So it has this inst and end inst instruction and end instruction. So what I'm doing here is I'm basically fine-tuning the model to have a different chat format. And actually, if I'm doing that, it is important to turn on this here. So let's see if I can, oops, that's the cell I wasn't supposed to run. Let's see if I can apply the adapters. Untype. It's giving me grief on which adapters. I'm just going to move ahead on it, but you do need to train the embeds, LM head and embed tokens, because otherwise you're not going to be able to update the chat template, given that it often moves around special tokens. So anyway, I've loaded a data set here. I'm just loading 100 rows, and I'm only loading 10 rows of the test set. And then I have my train and my eval. So you can see here, there's just one column called text. So I'm just feeding in this raw text. You can actually feed in messages, and it will automatically apply the chat template that the tokenizer has. So that's a method that I use in a lot of my other videos, and it's probably more robust. But here you can just fully format it in the data set itself. And so then we'll move to TRL, and you can see this is SFT config. This is now being used in the latest or in the dev version of TRL. So that's why I have the dev version installed. The docs are very good if you want to check them out here. So I'm going to do some training on this chat dataset with the model that I've loaded, with the training and eval datasets, and with the tokenizer I've loaded. In the args, I usually like to set the max steps to 1 just for a test, but I've actually only got a small amount of data, so I can run all of it. Now, I've got a max sequence length set. I'm going to be training using the test column here of this data. Throw any questions in if you have any. I'm going to train for 1 epoch, so a few quick comments on epochs. Generally, I love training for 1 epoch. I think that you're less likely to overfit. You can do multiple epochs if you don't want to generate more data and you find that your loss is still falling. But if that's the case, maybe you should have used a higher learning rate in the first place. I would generally keep increasing the learning rate until you find that the training loss becomes unstable. So that's usually my heuristic. But yeah, 1, 2, or 3 are kind of the values of epochs I'm thinking of. My train size and my eval batch size. So you want this to be as high as possible from an efficiency standpoint, because it means you're using the parallel capabilities of the GPU. So you want to increase this until you run out of GPU VRAM. I probably won't run out because this is a small model. But yeah, I like to have a batch size of 32. And that is because if you have many data samples, the model is averaging when it does a backward pass over those 32 samples. So even if there's one noisy sample, it'll smooth that out and it'll make your training a lot more stable. So 32 is kind of a good number. I will note that if there's a very small data set that you have and you want to encode some more specific information, that averaging can go against you because the model won't see any specific row of data at a time. It's just seeing batches of the full, 32 I said. So you're basically giving less granular data by doing more batching, which means you can't encode if there's a lot of nuance in a specific row, but you're going to have a less noisy training. So yeah, generally 32, but maybe with function calling, I sometimes do lower because I want to encode more specific info. Now, if you start running out of VRAM and you can't increase up to 32, the way to do that is you instead increase the gradient accumulation. So instead of just having 32 for your training batch size, you'll have a virtual batch size of 32 by doing a gradient accumulation of 4 and then a training batch size of 8. And all the gradient accumulation does is it says to the training loop, okay, go forward on a batch of 8. And instead of going backward, just do the next batch of 8. And instead of going backward, do the next batch of 8. And instead of going backward, do the 4th batch of 8. And after 4 batches of 8 forward, now you can average across the gradients and backward pass. So it has the same effect as doing a forward pass with a batch of 32, but because you're only doing 8 at a time, you need less VRAM. So that's your solution. I'm doing evaluation, which is why I set the eval batch size. I'm going to come to the questions just in a sec. Learning rate scheduler, I've got constant, so I've just got a constant learning rate, 1e minus 4 in this case. My evaluation strategy is going to be defined in terms of total steps. And that means here every 0.2, so every 20% of the steps. So if I've got 10 steps of training, it's going to evaluate every 2 steps. Warm-up ratio, this is where we're slowly going to ramp the learning rate so that we don't throw the model off kilter. Then we'll reach the actual learning rate of 1e minus 4, and then we're going to be constant. So that's the warm-up ratio. Output dir just means we're going to write results locally. Gradient checkpointing. This is important for reducing VRAM. It means that on the forward pass, there will be activations that are tossed away and they're actually recalculated on the backward pass. So the model in layers, it's kind of broken into chunks with a few checkpoints and the gaps are thrown away. That's inefficient because you have to recompute again, but it means that you need to store less data and that reduces VRAM. So yeah, I actually ran this earlier and I ran out of VRAM when I had this false. So it can make quite a big difference. I guess my batch size is very large. Well, fairly large for one GPU, like a small GPU. That's what I mean. It's large for a small GPU, even though it's a small model. And logging steps will just show the number of steps. So I'm going to run this here and see if it runs. By the way, PFT config, you can just pass in the PFT configuration. We actually applied it to the model. So here we ran get PEFT config. The reason I did that is because I wanted to show you the trainable parameters. But instead of running this line here, you could just pass the LoRA config. So you could just directly pass LoRA config into the model down here. And yeah, actually, the way to do that would be to just pass in LoRA config like this. So yeah, that's an option. It's like we have an error. And not quite sure what that is. So I ran it fine earlier. Let me take a few questions. Just let me run this all again. Make sure I didn't mess anything up. So flash attention is turned off. The model is fine. Do I have everything okay here? Okay, Proj, this here. I'll comment all out so nobody runs it like I did. You can calculate alpha if you want. And here we will print the train parameters, 2%. Load the data set. This may not work. I may not have time to debug because I prefer to answer a few questions. Let's see what happens. All right, let's work backwards. With max tokens to 204 ends, yeah, that might be an issue. If you have some data that here is longer, so you can see actually the longest sequence here in my data set is only 2,900 characters, not tokens. So yeah, I'm probably okay with my length in that case. If that's your question, Loic, you can clarify. What happens if you fine tune for instruct and have a big context before the query? If you fine tune for instruct, yeah, that might still be fine. That might still be fine. The reason why you would want to train on the prompt part is if there's actually knowledge in the prompt and it's useful for the model to learn from the prompt pattern. It's actually very inefficient to train only on completions. If you train only on completions, then you are not making use of all the compute you did on the forward pass because you're forward passing through everything. So it's pretty inefficient to just train on the completions, and that's why you only do it usually in the latter stages of fine tuning. But yeah, I think it still probably would perform fine. And we've some other question here on AWQ. When they say you fine tune 4-bit quantized model and merge it to 16-bit, performance decreases slightly. So when I quantize the merged model to 4-bit, does performance increase? Yeah, so this is getting technical, but it is covered in the video I have on LoRA. And you can check out a video. It's actually, the slides are from the video called Full Fine Tuning versus LoRA. And I describe exactly there the trade-offs that are happening that you're describing. But basically, the base model is 16 bits. The adapters are always 16 bits. If you go to a quantized model, the base model moves down to be 4 bits. Actually, this one here. But the adapters are still in 16 bits. So this is how LoRA works. And when you merge, you can do two things. You can either quantize these adapters and merge it down, which will hurt performance, or you can dequantize this base model. So basically expand it back up to 16 bits precision and then merge on top of it. That's the highest precision thing you can do. And that should not have an additional loss. And that actually we talked about at the very start of the video. OneSloth allows for that natively. And now you can dequantize using transformers. If you check back through some of my newsletters, here it is actually. Transformers supports dequantizing. Until now, a major drawback of LoRA was that trained adapters could not easily be merged. But yeah, they can be merged. There's this feature now for dequantizing. And this is the code here. So yeah, there's also a video I made specifically on merging, which was made before this dequantization was possible. But yeah, that should answer the question. Okay, folks, that's it for this week. Thanks for joining. And I'm going to fix up this spreadsheet now, or rather the collab. So if you check out the link in a bit, I'll make sure it's running. Thanks for joining, folks. Cheers.